Okay, so I think we are ready to start the afternoon talk. And the presenter today is Shivangi Pandey, who started her PhD in 2021. She completed the thesis, but she submitted the thesis, but she's about to defend. And she joined here our institute as a research assistant for the moment. I hope to have her much longer as a postdoc as well. She was doing her PhD with Dr. Subendu Rakshid, and she will tell us what she was doing before joining Warsaw. Floor is yours.
Okay, so good afternoon, everyone. Today I'll be discussing about the central region of active galactic nuclei through optical spectroscopy. This is also my PhD thesis topic, and so I will be presenting the projects that I have led during my PhD. Okay, all right. So this is the how the talk is organized. So first I will just briefly introduce the active galactic nuclei properties and their components. And then what is the motivation and then related aim for different projects. And then what amount of data and from where I have used the data and how I have observed, what are the facilities that I have used, then some methods and analysis tools. So the first project will be about radio loud AGNs, studying them and how to measure their black hole masses. Also, how the jet, which is prominent in radio loud AGNs, how to decompose their contribution to get a better BLR lag and hence the black hole mass and continuum luminosity. Then another work is about using AGNs as distance indicators and how we can use them to constrain the increasing Hubble constant tension using the amalgamation of two different techniques, which is spectrometry and reverberation mapping. And then finally conclusion and future prospects. So to introduce the active galactic nuclei, I would like us to imagine a host galaxy which is spread into tens of kiloparsec scale. And so the stars are located in the disk, but at the very center, there is a highly energetic region, which is active galactic nucleus. So when you zoom in more to hundreds of parsec, you will first encounter narrow line region, which are ionized gas clouds moving in hundreds of kilometers per second under the influence of a core. When you zoom in more to a few parsec scale, you will encounter this dusty torus, which is a ring or clumpy-like structure having dust and molecules. Then when you zoom in more to sub-parsec scale, sub-parsec scale, you will encounter this broad-line region, which is a dense gas cloud in a faster Keplerian motion around the center. And they are moving with the thousands of kilometers per second speed. So if we can study the broadline region, kinematics and geometry, it can actually infer the inner, we can actually infer the inner structure of the AGN, as well as we can encode the black hole mass measurement as well. So this is one of the most important component on which I have worked on during my thesis. So I will mention this particular component a lot in the following slides. And then when you zoom in more to milliparsec, you will see the central core, which is consisting of the supermassive black hole at the center and the accretion disk, where the matter is losing the angular momentum and converting the gravitational energy into radiation. This radiation is actually the powerhouse of AGNs, which lights up the NLR, ionize the BLR, and sometimes also shoots jets out of the system and displays. So in entirety, this is how the AGN looks like with all its components. So as I said, the AGNs are powered by supermassive black hole at the center. Luminosity and mass is exceeding this range. then it is emitting an abundant amount of radiation in broad range of electromagnetic region, and it shows flux variation over time scale of months to years. Also, the AGNs are characterized on the basis of viewing angle and spectral features. For example, type 1 AGNs are those which when we look at them on a face-on view, one could have narrow and broad emission line features in its spectrum. And if we are having an edge-on view, then dusty torus is hiding the inner part, which is the BLR. So one can only have narrow line features in the spectrum. Okay, so moving on from the introduction, I'll talk about now the main motivation of the projects that I have led. The main motivation is measuring the black hole mass. Why we want to do that is because in here left side you can see a plot between black hole mass that is measured, and with respect to the stellar velocity dispersion value. And you can see that both of these things are very well correlated. So it suggests that maybe these black hole masses which are sitting at the center are influencing the host galaxy, or maybe their growth or evolution are interlinked. So AGNs give us an opportunity, gives us an opportunity to study the co-evolution and growth history of these SMBHs and their host galaxies, and hence to study the evolution of the universe. But it is difficult because these central engines are highly compact, and we need a few micro arc second of resolution. So and then they are also unresolved even at low redshifts. So dynamical stellar modeling is out of the question for most of the parts. So we replace spatial resolution with time resolution, and there we have this technique called reverberation mapping. What is reverberation mapping, short for RM? So it usually infers the size and structure of the BLR by observing the response of emission lines to the continuum variation from the center source. So here my concerned region is BLR. One can do the same for accretion disk and dusty torus. So for example, this is the core, and it is giving out radiation in every direction all the time. The moment it hits the nearby gas cloud, it photoionizes it and gives out emission line. So for the observer, there will be two light curves. One is the continuum, and another one will be the emission line light curve, which will be a lagged version of the continuum. This lag is actually coming when the light is moving from center. It is just a light traveling time from center to the nearby gas cloud. So when you multiply the lag with speed of light, you can get the average BLR size. So the next thing is this thing actually can infer the black hole mass by using Virial theorem. Obviously, there are other components as well that goes into the formula. Except for BLR size, the another parameter is the line width. So line width we get from spectrum. And for example, we have this edge beta emission line. We measure its FWHM, or standard deviation, that goes in here. The third component is the virial factor that is dependent upon the kinematics and geometry of the BLR. We can infer this parameter if we can do dynamical modeling. For this, we need to have good data. And so this can also be a reason of high uncertainty in the black holes. All right, so having said that, I will just briefly introduce what are the objectives that I would like to lead. So you can see that here, this is a plot between BLR size, which have been measured by using reverberation mapping on around hundreds of sources till now, with respect to continuum luminosity at 5100 angstrom. So if we can have a scaling relation, if we can establish and calibrate this particular relations, the BLR size to luminosity relation properly, we can actually estimate the black hole mass by just using a single epoch spectrum. this will make our life so much easier of having to do the time-intensive observations for high redshift AGNs and many other things. So we need to calibrate this scaling relation. But there is a problem that in the low luminous region, the AGNs are less explored because of the host galaxy light contamination. And the other thing is they also have low variability. So that is the issue. And then another problem is the high accreting AGNs, which are deviating from this relation. Another thing is the radio loud AGNs, which have jet impact. So in the optical continuum that we are getting, it will be a contribution from jet and the disk. So we need to separate the jet optical emission to the disk so that we can infer the BLR size properly. These are the objectives, as I said. And lastly, how these AGNs can be used for cosmology to constrain the Hubble constant. So these are the objectives. So now I'll talk about the data on which I have worked on. So I have also taken archival survey data from STSS, the multi-year high cadence data from Fizyki transient facility, ASASSM survey telescope, and then radio data from Pawan's observatory and Fermi-Lat and gamma ray data from Fermi-Lat. And I've also used polarimetry data from Steward Observatory. Along with the archival data, I've also observed many number of AGNs using these telescopes, which are present in India. The first one is 1.3 meter Diesel fast telescope, which is mainly used for photometry.
Is it really in Himalaya? Because the name of the telescope is Himalayan.
Oh, this.
So do you go to 8,000?
No.
It's in Ladakh. So it is remotely used by Bangalore facilities. So we can just remotely use. Go to
So you
Bangalore
even
Yes,
do not go
Even
there.
if you go there, the height is close to 4,000 meters.
4,000.
Not 8,000.
But people go there. But
Yes,
it can be.
Himalaya. Okay.
All right. So I have used 2 meter Himalayan Chandra telescope, which is in Ladakh, and 3.6 meter and 1.3 in Aries, Nainital. They have IR and optical spectrographs, so we can do spectroscopy. Okay, all right. So these are the data that I have used. I'll just briefly just mention that I have extensively done the Leica modeling, use the parallax method, and the data reduction tools for photometry and spectroscopic data using some softwares which are very well known, such as IRF, Dark Extractor. I've done time-lag analysis using many different methods and simulations, and also used host galaxy decomposition software Galfit for low luminous AGNs. So now I will start with the first project, which is about studying the radio loud AGN and their mass measurement, and how the decomposition of jet and disk emission to improve the VLR region size. So for this work, I have used 2 radio loud sources because they have long-term monitoring data available, and they have pronounced jet activity. So
But they are not blazars, right? Because you must see the broad line.
Yes, and the emission line is also important. So PKS 1510 is already been previously studied by Rakshit et al. 2020, and it's the H beta BLR size and black hole mass is measured to be of this value. But for PK 0736, we do not have these measurements. So as a first part of this work is to get the black hole mass and unknown BLR size. So for this, I have used Steward Observatory data, having optical V-band photometry and spectroscopic data points. These data points were around 130 and 133. So, and then additional to the optical data points, I have also used gamma ray light curve just to see where there is a prominent jet activity. So By having procured the hundreds of spectra of this source, what I have done is this is how a spectrum of a agent look like, having different emission lines, component, and continuums. So what we do here is we model the continuum with power law, and that continuum will be subtracted from the entire spectrum, leaving behind only the emission lines. Then we model these emission lines with different combination of Gaussians, and then we integrate it to get the respective emission line fluxes. For example, for H beta over here, since we have hundreds of spectra for it, so we will have hundreds of H beta emission fluxes over time, which will constitute a light curve. So here I'm showing the light curves for this source. So top panel is the gamma ray light curve. The second panel is the photometric V-band light curve from Steward Observatory. And then from the spectrum, I've also calculated the flux at 5100 angstrom, which is also denoting the optical region. And then H beta and H gamma emission line fluxes also calculated, as I have mentioned earlier. And then radio flux, and the last one I'll talk about later. So from this from these light curve, you can very well see that there is a very prominent jet activity, which is reflected in the optical light curve, but it is not so in the emission line fluxes. So definitely, if we'll do the lag analysis, that is the correlation study between the continuum and the emission line, this region will be problematic. So we eliminated this region and only work with the present state to estimate the size of the BLR.
Because jet does not illuminate the broad-time
broad
region, right? It directs the
Yes. So
flux in vertical direction, while
yes, so we
broad-time
assume that the
region
BLR
is
is only affected by the accretion disk continuum, not the jet. So for correlating the continuum and the emission line light curve, I have used ICCF, which is the cross correlation method, and another method was Javelin. So what Javelin does is it models the continuum light curve with damned random work, and then it assumes a transfer function, which is just a signature of how the BLR will react when the continuum arrives. So when this transfer function is convolved with this modeled continuum, it will give out a shifted and lagged and amplified version of the emission line flux. So
and this transfer function is some sort of a Gaussian or what, or something more fancy?
Javelin usually takes top hat. Top hat, yes.
Like this?
Yes.
Okay.
But there are other methods also which have a liberty of choosing your different transfer functions. So now that we have the lag of around 70 days, the another parameter to estimate the black hole mass is the line width. So for that, we have constructed mean and RMS spectrum from all the hundreds.
But you have also 200 days, right?
Yes, I have taken, like, I have correlated these light curves by taking a window of around 300 days, so that we can know that whether there is some seasonal changes.
So this 200 days is an artifact, or
it must be because of the seasonal effect, like every 6 months. Because the data was for more than 300, 500 days, so that's it. Okay, so for line width estimation, we have measured the FWHM of H beta. Sorry, of FWHM is standard deviation of H beta, and then we have inferred the black hole mass of this value for this particular source. Now we've completed the first part of this project. The second part is to know that whether this optical continuum emission is contaminated by the jet or not, even in the quiescent state. So for that, what we have is we have measured a non-thermal dominance parameter. It is actually a section of observed total optical continuum to the predictive predicted optical continum. So what is this actually is the observed optical luminosity will be a combination of thermal contribution coming from the disk and non-thermal contribution coming from the jet. But this predicted one can be measured by this empirical relation that has been established by Rakshit et al. Using SDSS-DR14 catalog. So here, as we assume that H beta can only be inferred, can only be correlated with the, or can only be illuminated by the continuum that is coming from the disk, not by the jet. So whatever the flux we are having from H beta, it will give us the disk continuum flux. So the predicted one is this, and the total one is having both of thermal and non-thermal part. So if this particular NTD is greater than 2, we say that obviously the jet is contributing more than 50%. So from here in this plot, you can see that when the continuum flux is increasing, the H beta flux is not getting affected, especially at this region when the NTD is greater than 2. That means the H beta flux is not affected by the jet contribution, the increasing jet contribution. This is similarly seen in PKS 1510 as well. And so for decomposing the thermal and non-thermal part in the continuum, I have.
But you have a spectrum, so don't you see the jet contamination in the slope of the spectrum? Too difficult?
Yeah, it's difficult because like there will be lots of contribution in the spectrum from different emission lines like FP2 and all, so we cannot modulate.
Okay.
So for decomposing it, I have used polarization data as well, along with the optical V-band data from Steward Observatory with the same baseline and same almost same cadence. Then I've also used OVRO 15 gigahertz radio data as a signature for jet. And then there is this software which is DCOM developed by Lee et al. 2020. Which is a combination of Bayesian inference framework and the damped random walk. So what this software do is that it assumes that the total continuum is obviously the combination of disk and the jet part, and then it models both of these continuums by DRW, the damped random walk model, and then assumes the transfer function which is related to H beta and the radio. And then it models the both of these light curves as well. After modeling all 3 of these light curves, it also takes the polarization data and models it, and then gives us different parameters. So here I'm showing the results for the decomposed part of jet and disk, along with the total optical light curve for both of these sources, and how they are modeled, the H beta and radio light curve, how are they modeled from this code. And then what are the posterior values for all these different parameters. The most important ones are the H beta lag and radio lag. From these values, you can infer that the radio region is much farther away from the H beta region.
So it's a random walk in a parameter space of how many dimensions?
So the parameter space is basically, so these are the 3 parameters. For example, the random walk model will have 2 parameters. One is the amplitude, and the another one is the damped time scale when it loses the information.
But anyway, there is a problem here, because if for the accretion disk, damped random walk is not a bad approximation. But
Yeah.
for a jet, I think it is. At least you should calculate the power spectrum first, or the structure function, and see if damped random walk looks like a good representation of variability. I think it does not.
Yeah, in many
And that's
cases.
immediately a problem.
Because this is new terminology to me. I am making a lot of assumptions on what damped random walk means.
Damped random walk is something which in the power spectrum shows flat thing and then steepens to -2.
Okay,
It's very specific thing.
okay.
And it really applies more or less to AGN, although not quite. But it's not a catastrophe. -2 is okay. Then 0 is not quite. It's more like -1, but
But then the purpose is
but
to
if you
recover
look
the-
at jet variability, you see spikes. So I did not calculate the power spectrum, but this is the first thing which you should do, and it will look like a problem anyway, because it's spiky.
Yeah, for many AGNs, DRW failed to model the.
So,
For
you
blazers,
have
for
some-
blazers, people do not use
Yeah,
damped
for
random
blazers.
walk, I think.
I think my question is even more basic than that. Is you have a merit function, so you want to compare something and say, is this a good guess? And then if not, you
So
throw
we
throw a
have,
coin
so-
or a
yes, so we
die.
have a light curve and how you can predict the next step of it, or how the past observation.
So how many? And you need 2 parameters to do that.
Yeah, for damped random walk, there are 2 parameters.
And everything else is, let's say, derived from those, because I
Yes,
see that
yes,
you have
yes.
like
The around 5 to 6 parameters here are 3 parameters, and these parameters are somehow a fraction of related to this. So this FT is basically the disk fraction, that is the total disk emission out of the total optical emission we have. So it constrains this parameter by modeling the polarization data, like the angle and the degree, and these different ionization, this different polarization parameters like I, Q, U, and V. So it models all these things, and then somehow it gives the average value of degree and angle and the fraction.
Yeah, because we know that walking randomly in a space of, like n dimensions, it's a bad idea, but it's a very inefficient way.
That's
No,
why
and
We still do it
Yeah,
sometimes.
this
because we
this
have no
damped
choice,
random
right?
this damped
But-
random walk, you can understand mathematically in a very simple way, but then you see that it's quite strange. If you imagine that you have a function which looks like that, here you have flux, here you have time. If you have an instantaneous flare with exponential decay, and then if you have random number of such things, you will produce damped random walk. So it's highly asymmetric flare.
and it's stochastic.
So even by eye, you see those things are not highly asymmetric. If you do something like that, you will get something different. Only this thing, highly asymmetric, when you calculate the power spectrum, will give you this kind of 0, -2. If you imagine something which is exactly symmetric, then you will have -4 here. And it will not be a damped random walk.
It's extremely.
So it's very
proposal.
strange thing, which by pure accident, I would say, slightly mimic AGNs, although in reality, in AGNs, you do not see things like this. You see more or less things like this, and then 0. And this is not exactly -2. From Kepler data, it's -2.3 in the optical band. But for blazers, it's extremely dangerous. So, but this is the simplest thing, right? And the exponential. And then you can calculate the power spectrum analytically. This was the experiment I gave to students during my lecture, because you calculate Fourier transform of a single thing, just one function, analytical. So excellent, but simplistic.
For these two sources, I have found that in PK 0736, jet dominates at around 70% of the total optical emission. And for PKS 1510, the disk emission is higher comparable to the non-thermal optical contribution from the jet, which was about 30%. And then here these two plots are just showing how the disk and jet fraction is varying with respect to time. And similarly, both of these sources are how they are placed and how they're moved with the true luminosity, that is after removing the jet component. But since you can see that both of these sources are still deviating from this RN relation, so it shows that even with radio jet effect correction, both of these sources still deviates. This suggests that radio loudness might not be impacting the deviation of the sources from the scaling equation. So we need to know what else is there.
But do you have an estimate of the Eddington ratio for those two sources, and it's not high?
Yeah, it's mildly high, not very. They are not very. It comes into higher frequencies. So Eddington ratio as well, and then FP2 is also a signature of high accretion. So
because if you say that all those high Eddington ratio sources are below, and that one is also below, then
we can sort this out with another parameter in the scaling parameter. All right, so another project is about measuring the geometric distance using AGNs. And this is just a reverberation mapping monitoring of these two sources. So the first of all is that accurate distance measurement is crucial in astronomy and cosmology, which addresses the Hubble constant tension. So for that, I have used, there are two techniques which can be act as a combination. So the first one is spectroastrometry combined with reverberation mapping, which is closely called as SARM technique. So for this, why we are using AGNs, because they are promising for accurate distance estimation up to redshift of 7, and there is no requirement of extra what should I say? It's an independent method because it's an independent geometric method, so doesn't need any other confirmation for this, like other Hubble constant tension methods, like using supernovae or CTPs. So the spectroastrometry is just measuring the spatial displacement of different parts of the source as a function of wavelength. So here in this diagram, I'm showing you that how this can use to get the angular distance and hence the Hubble constant. So from reverberation mapping, one can get approximate estimation of the BLR physical size. And from spectroastrometry, one can get the angular size of this source. So by just using the parallax method, you can get the angular distance of this source to us, and then Hubble constant. Right. So this SARM usually combines the angular and linear BLR size measurements to finally get the distance. So the spectroastrometry is usually can be done by a spectroastrometer or an interferometer. Here, gravity is doing it, and it has observed a handful of AGNs. So it has resolved handful of AGNs, dusty torus, and a few BLRs in the case of 3C273. So this SARM technique was first applied by Wang et al. 2020, who measured the angular distance of 3C273 with this angular distance of 500 megaparsec and Hubble constant of this value. Wang also proposed around 30 AGNs having lower redshift that can be constrained within 5 to 6 months of monitoring, taking care of the magnitude K-band limit of gravity. And they have also simulated the data and predicted that the Hubble constant can be constant value can be achieved with a precision less than 3%. So till now, this SARM technique has been used on handful of sources, around 4 or 5 sources, and this is the angular distance to redshift plot, and these are the sources that are located in this curve. So hopefully we can add more. So for that, out of 30, I have chosen 7 AGNs to be observed. That is depending upon the northern and southern declination limit, because the gravity interferometer that is present in southern hemisphere and the telescope that we were using are in northern hemisphere. So the declination, so we can only choose those sources which are having declination above -15 degrees, and also taking care of the K-band limit of the sources because of gravity observations. So we expect that the lag will be less than 30 days, and it can be so monitored within 5 to 8 months of observations. And we hope to get the spectroscopic monitoring for different fluxes and different emission line region for these sources. So we have observed these 7 sources from 3.6 meter dot in Nainital and 2 meter HCT in Ladakh. And out of 7, we have successfully observed for 4 sources. And then out of 4 sources, only 2 sources were there for which the light curve was showing variations. So we have from 7, we have 2 sources. Here I'm just showing that how these AGNs are looking from in the band images of 2 meter NCT. So reduction, spectroscopic and photometric reduction has been done by using different softwares. And here I'm presenting the spectra from different spectrographs. And you can see that the H alpha and H beta in different narrow emission lines are very prominent in both of these sources. So here also similarly, we modeled the continuum with power law, subtracted it. Then the emission lines were modeled with different combination of Gaussians and then integrated together fluxes. So here I'm showing the light curve for MRK 618. The optical data points were a combination of the observed fluxes as well as the data points available in ASSN and ZTF. This continuum light curve is correlated with H beta and H alpha, and these two are the lag histograms using different methods such as ICCF and Javelin. So we measured the H alpha and H beta lag with respect to the G band continuum. Similarly for this source as well. And here I'm just showing that what are the different lag values that we have obtained using different methods. And for line width estimation, FWH and standard deviation calculation for H beta and H alpha. And so using different combination of mean, RMS, and line width, we have got different black hole masses. And so we adopted the black hole mass from RMS spectrum. And so the MRK 1048 is around 5 times higher than 618. So this was the first part of this project. The second part was getting the spectroastrometry data from gravity. But unfortunately, at that time, we couldn't get the observations. So there is another software which actually simulates the spectroastrometry signal. It models the VLR and could also predict the expected angular size from the API. So this is the expected angular size accounting for different emission line regions. So hopefully with the new generation gravity plus, it will observe hundreds of AGNs. So maybe we can get the data for these sources as well. So similarly for these two sources also I have plotted them in RL relations. This is for H alpha and this is for H beta, and they are showing very mild offset. So this is possibly because of different VLR structure and ionization differences in these two sources. So yes, and then adding a source in a low luminous region, I have also studied the NBC 4395, which is a very peculiar intermediate mass black hole. And for this, I have observed the source for simultaneously 2 days using 3 telescopes present in Aries. And measured is its first spectroscopic H alpha lag, which was about which was about 125 light minutes, and the black hole mass from this method was around 20,000 solar masses. Obviously, studying IMBH is very important because they are known to be the supermassive black hole seeds at early universe. So we can understand that as well. And also, if we can add more number of IMBH study, we can also know that whether different scaling relation or empirical relations are also valid in low luminous region. So as a summary and as a conclusion, I would just like to mention that the work that I have done, somehow extends and advances our understanding of VLR size luminosity regime in high and low luminous regions in the RL plot, and also presents a pilot study using AGN as standard candles to probe Hubble constant. So hopefully for future work, one can use high quality SDSS RM sample and could model the BLR with upcoming softwares, and then using gravity plus the next generation interferometer to get the spectroestimetric measurement and constrain the BLR parameters, and hence address the question of Hubble constant. And then we can also use foremost and LSST for aging variability studies, different other things. So yes, yeah, this was my group in Aries, and this is Aries.
Okay, thank you. Some more questions?
I'm sorry.
No, you first.
Mine is very quickly. What would bring foremost to your pipeline that you can get?
So foremost is obviously a survey telescope. So there is a program of collecting. Obviously, it will collect observations and spectroscopic observations of lots of AGNs with the higher redshifts. Yes, so with higher redshifts, and it might be there for like more than 5 years. So there is also a very peculiar program for foremost, which is the TIDES RM. This will take the spectroscopic observation from foremost telescope, and it will combine it with gravity and other modeling stuff to constrain the Hubble constant. So
I think because Maciej Fizyki, who gave the talk last week, last time, he is now in charge of receiving the applications for foremost before the operation starts. So he warned us that, you know, the operation will start soon. So of course, if you want to propose a specific project, I think now is the time.
yeah, yeah,
Because I
similarly-
know this is probably already involved.
Yes.
But it's not, he would be the person collecting the applications before the observations start being taken. I think would be an nice.
So maybe you can talk to Maciej, because I'm not involved in most, so I don't know. And okay, next question.
Okay, so my question is about the variability of the jet, because I would like to understand the argument. So in typical scenario, the jet power is depending on the spin of the black hole and the mass accretion rate. And as I can imagine, and if we have a quasar of AGN, when we have this moment when the AGN has larger luminosity, we we expect that there is a larger m dot mass accretion rate, and then we should observe it in jet the same behavior. So it means that the time scale of the variability in accretion disk, it should be imprinted in jet, right?
Yes.
This is exactly, these are, okay, good, okay. So maybe.
Well, yes, and but this is not surely the whole story, right? So if you have a variability in the accretion disk, it propagates into a jet. On the other hand, inside the jet, you have a lot of shocks,
Yes.
substructure, and magnetic field reconnection. So on top of that, you have imposed a much faster variability.
Yes.
So this is why in jet you see spikes. It does not look like optical variation.
But
So the amplitude is much higher in jet.
Yeah, but
particularly in blazar.
okay, but can we find the imprint of the variability in the optical wavelengths in jet, in radio?
So like I showed you the light curve, which was replicating when there was a pairing region, it was quietly replicating in the optical region as well.
Okay.
So obviously that was the whole point, that the optical or emission that we are observing will be a combination of jet and disk. That is non-thermal contribution from the jet and thermal contribution from the disk. That is why we want to separate both of these things.
Okay, thank you.
Yeah, so it sort of accumulates because in the accretion disk, you have slow variations at the outer radius, and then you add, those propagate, but then you add shorter and shorter timescale variability close to the black hole, and then you go to the jet, and then you add still more short timescale events.
Yes, sure.
So you have to calculate the whole history of the flow in principle.
I have a question that all of this should depend upon the spectral state of the system. And a related question that you have also not, you mentioned something about that you could not model.
Yeah.
So what about the spectral states? I mean, and why no modeling? Because you had the light curves, but
I mean, I don't know.
like spectral modeling.
Yes.
You said that
modeling.
you could not model.
Yeah, so the thing is like in the spectrum, you will see a continuum. That continuum will be a contribution from many
Both the
other
components.
things. Yeah, many other
But
things.
like you can,
So that was the issue, like what kind of model will be using
so,
for jet.
so,
So that is why polarization come into it. Because we assume that the polarization is the signature of a jet.
Yeah.
And usually for a face on geometry, the disk polarization contribution is very less. So that's how we have polarizations in nature interview, and so it separates.
So you're saying that to understand the situation, this was a better option than
This
the
was a
spectral
better
model.
option.
Because
Yeah, in addition, the problem is that from the accretion disk, you know more or less what to expect. You expect blue spectrum, right?
Yes.
Yeah.
But then you can have some extinction effect. So then it will be flatter, redder. Then from the blazar, you have those synchrotron components, and then it's not obvious unless you have full SED where they do peak. So this stupid thing has two slopes and it moves across the spectrum.
Yeah.
So you are not quite sure whether it enters like this or like that to your spectrum. So you have, if you, yeah, like she has a relatively narrow, because all optical is a relatively narrow band, then you don't know.
So if you have an SED, you can also model the jet component and the
Yes. Yes, then you can eventually decompose things much more reliably. But then you need really all radio, all gamma ray, whatever, X-ray to know exactly where those two bumps are.
I also have a technical question. If you could show the results of that Mark A, Mark B, just clarification about the width of hydrogen alpha and beta line. Yeah, no, there, You
Yeah.
had the chi-square.
Yes.
Yeah, why are these chi-square like 0 point something? Usually we take 1 point something, close to 1.
It's
like it
actually,
fits.
this chi-square is a combined value for all these Gaussian fit, not just for one. So that's how this is affecting. If only one Gaussian fit is there, maybe the value is higher. So it's
So
just
what
getting
does
added.
that kind of chi-square value tell us? Like if like in say if it's model any one signal, then we say that okay, if it's less than 1, it's overfitted. If it's greater than 1, close to 1, then good fit. Greater than 1, then bad fit.
Yeah,
What
so
about these
it's a better fit
Okay.
because it combines all these things like the narrow emission lines and broad emission lines. So it's a collective value for the fit. So that's how it gets reduced.
And anyway, it's quite difficult to calculate chi-square because estimate of the error in optical data is quite tricky.
Quite.
Because in X-rays, you take the square root of the concentrate and that's it.
Yeah.
I tried that in the optical band. Then I usually get chi-square, which is much larger than 1. So if you want to get fancy result, you regulate your error in the optical band to get chi-square 1, but it's kind of cheating.
Yes, because it does a lots of simulations. So that's also like maybe the error budget is.
Okay, thank you.
It's kind of hidden
Point
systematic error in data analysis.
So your study is more like a multi-wavelength study, not just optical. Right?
Not just optical, because like this 10 spec, this is an IR spectrum.
Yeah, you also have that.
Yes.
Okay, more questions, comments? Okay, so let's thank Shivangi again.